Okay, let me just quickly get through this session because it's going to be a little bit technical. So earlier, we've learned about the non-determinism in LLMs that creates really a lot of challenges for how we incorporate AI-first software delivery, right? Now we'll dive deeper into LLMs and really understand what's causing that non-determinism. And finally, we'll hear about a new LLM decoding method that improves over existing methods. Methods that you have used in your open source models, in your API-based endpoints. So this is a new method. And it really makes the outputs more reliable, more accurate. It's more efficient in generating those outputs and can be used for tasks, including AI-assisted coding. So this is something that all of us know. AI outputs are really non-deterministic. And what does that really mean? For any given input, an LLM generates outputs, text, that are really probabilistic, stochastic, unpredictable. It's just a lot of possible combinations of words, tokens, one after another. And why does this really happen? There are a lot of statistical distributions that governs how these tokens are sampled and chosen for the next step, occurring recursively until we reach the end of the text. And what is this distribution all about? In any given language, or the corpus that you are using, that language can be English, Hindi, can be programming language. There's a set of vocabulary. And that set of vocabulary are the words or the tokens. And typically, there's about 20,000 to 200,000 of those tokens, depending on the tokenizer that you are using. As we can see in this example, if we input a dog is A to an LLM, it gives you a lot of possible outputs. Friend, canine, maybe cat, maybe bundle, right, of joy for the next 2 and 3rd words. So let's stick to this example. What is this statistical distribution in terms of what we can visualize? Using this probability distribution chart, it really makes sense once we can visualize that friend, canine, and bundle are the possible tokens that make more sense than, for example, cat. A dog definitely can be a cat to people who are animal lovers. To someone who loves a dog as much as a cat, it can be either, right? They are both lovely animals. But it's probably something that's less likely for us to encounter looking at the entire corpus that we see in the world. Let's quickly dive into some existing methods that generates next tokens in LLMs. So the first question that we need to ask ourselves is, there are up to 200,000 tokens. Does it really make sense to include all of them for generating the next token? That is the very big question that we need to ask ourselves. Smell, table. A dog is a smell, is a table. What, hey, and lots of these tokens in the vocabulary. And it turns out that no, the answer is no. Why is that the case? There are so many words that are of low probability and of low relevance to the text. If we include them in the sampling, the entire generation will be prone to incoherence or even hallucination. And the next question would be, which tokens do we then include? This is actually quite the unsolved problem of LLM decoding for both reliable, practical usage and satisfying theory. So this is the unsolved problem. which means that we try to make it better. We try to solve this problem incrementally. The golden question would be, how do we then determine the right tokens to be used for sampling? Running through some of the existing methods, real quick, top K and top P first. These are the methods that are available in your API methods. Right? You use OpenAI API, you use Mistral API, things like that. They would have these very traditional methods. Top K tokens, fix a parameter, 15 tokens. There you have, in this case, if your top K is set to 15, right? Top K, the parameter K, you set to 15, you believe it is 15, you have up to 15 tokens. You only consider the 15 tokens for sampling. Top P, we choose a cumulative probability. In this case, 95%. I believe that I should only include 95% of the entire token space. I'll look at the cumulative probability shown by the red line. In this case, I have a line over here that is 95%. I'll include all of these tokens up to this point. And I ignore the rest. That's your top P. Very traditional methods. And then there are some other methods. Epsilon sampling, I just define a minimum probability which I will use as the cutoff for any tokens not meeting it to be dropped from the sampling set, right? Which means that we are actually including all tokens here in the sampling. We're actually including all tokens here in the sampling because they are all above this line. MinP is another method that takes the highest probability here, multiplying it with a hyperparameter once again. And this is usually 10%. So 10% of 0.2 gives us 0.02 as the cutoff, right? Similarly, we are still including quite a number of tokens. In this case, up to 17 tokens, 0 to 16. And what are the disadvantages of such methods? The quality of the text produced is really sensitive to the hyperparameter that you choose. For example, top K, is it 20? Is it 15? Is it 25? How do you reason about it? Or is it just a heuristic that you justify using a certain data set that may not fully apply to your task at hand? Secondly, these methods do not consider the distribution shape. A distribution can be of a lot of different kinds of shapes, as you can see here. It could be very peaked. It could be very spread out. It could be something like this. But all these methods do is to apply a hyperparameter, right? It's fixed throughout the generation, regardless of what the distribution is. And that distribution can change in every single step. And of course, different tasks. It can be creative content generation. It can be your logical reasoning or solving math problem or even AI-assisted coding. Different tasks require careful tuning of these hyperparameters if you were to use these methods as your method for decoding text within your LLM, right? So you can get a more optimal performance besides your prompt engineering and things like that. So here's where we propose a new sampling method. And this is a method called P-less. P-less because it is without hyperparameters. It truly uses the entire distribution, an entire distribution to determine an appropriate threshold that looks at the entropy or the level of confidence of the distribution. It's given by the very simple equation that you see here, the summation of all the squared probabilities. Looking at this chart again, it is just a square of all these bars, squaring all these bars and adding them up all together to arrive at the threshold. And that is grounded in theory, in probability theory. So we define that as probabilities whose tokens, or rather tokens whose probabilities are at least this Peeler's threshold for sampling. Why is that the case? Because Peeler's quantity denotes the probability of a correct and random sampling, which is actually what we are doing when we sample, right? When we sample a next token using whatever methods, we do not know what's correct, we do not know what's desirable, we do not know what's non-desirable. What do we just do? We sample, right? So this gives us a threshold to tell us that it needs to be at least this threshold that the current distribution is telling me. And these are the 4 tokens that satisfy this constraint. These are the 4 tokens that meets this threshold for us to select for sampling. And now we have gone through some of the methods, the 4 methods on traditional sampling and the Peeler's method. Let us revisit the initial task we had for the LLM. We input into the LLM, a dog is A, right? And we see that there are so many possibilities. All are possible. The only difference lies in how probable, right? How probable would be the heights of their probability bars. And truly what we see here is that using the Peeler's method, it ignores all of this. A dog is a smell, a dog is a cat, a dog is a table, a dog is a what? Hey, right? It only includes these: friend, bundle, canine. And for the other methods, they include tokens all the way to even further than this distribution, right? Up to 200,000. This is just a very short version of what we will actually see. So using this method, different distributions, which is definitely what we will get in every single step of the LLM generation, will lead us to different thresholds. It adapts to the distribution, rather than saying top P is 0.95 all the way, rather than saying top K is 15 all the way. And this is grounded in theory, not simply a heuristic for AI or ML practice, but is interpretable using probability theory, entropies, and statistical moments, which you can refer to our research paper if you're interested, which we will be showing at the end of this presentation on the last slide. So there are other advantages if you are interested in ML engineering. So the threshold probability is automatically calculated, hyperparameter free. As an ML engineer, that saves you tuning for the hyperparameter. As an ML engineer or developer, this guarantees a non-empty set, which is great. Guarantees are great. No edge cases, right? This always produces a valid sampling set that is at least size 1, up to the entire size of the vocabulary, depending on the distribution. While other methods, like what we saw earlier, if the epsilon sampling, which is a minimum probability, is too high, there might be no tokens that satisfy that. And therefore, you end up with an empty set, producing some exceptions. Right? And this uses the empirical token distribution. This uses the empirical token distribution. You do not need to assume hyperparametric distributions that will introduce more noise to your LLM generation. And of course, it can be directly added to your LLM if you are using any open source LLM. And this is an example of how you would integrate it into your local LLM using the popular Hugging Face API. So if you see here, I have a model that I'm using, which is Llama 3 Instruct. I have a simple task for the model. Just perform this mathematical expression, 1 plus 2 minus 3 times 4 divided by 5. Simple operation, right? I load the model using the Hugging Face API. I put the task, this text, into the model. here gets the output. The output will be a distribution over the tokens, right? We got to sample again. We got to sample. And we sample using the P-less decoding function, which can be imported at the top here, right? So that decoding function is provided to you in our GitHub repository, which we'll be showing at the end of this presentation, the last slide again. Right? And once we decode one single token, append to the context, put the appended context back into the LLM. Repeat, generate using P-less decode, put back to the LLM until you get a last token. Right? If you are an ML engineer or developer, this will be straightforward for you. If you are curious about this is done using the P-less method. Luckily, it gives the correct answer, 0.6, right? And it actually tells you what you should be doing. Right? Do multiplication and division first. That's your basics. And then plus and minus. Doesn't matter where they occur, right? So it's interesting, right? Not only does it give you the correct answer, it shares with you the correct steps. And once again, this is non-deterministic. You run this over and over again, you get lots of different answers telling you the same final answer. Why? So we got to do something like this, right? We got to have a way to get our final answer, right? Produce our answer in a deterministic format here. The answer is 0.6. While the internals may be non-deterministic. The final answer is deterministic. Right. Further to this, I'm sharing some quick results with you on why this method is proven to be working. So we have tested this on many data sets, at least 4: creative writing, logical reasoning, math problem solving. And we found that P-less method indeed works better than the rest of the methods that I've shared with you earlier, and some other methods like Myrostat. Right? You can see that the top curve, that curve with the shaded circles, markers, is from the P-less method. It's always achieving higher accuracy than the other methods across a number of temperatures that we apply to the LLM. And this method also produces a good text diversity competitively. How do we see from this graph? For any accuracy level, P-less is producing a better text diversity. Right? So it would be more interesting and less robotic. Or for any diversity, P-less is producing a higher accuracy than the other methods. So it's lying at the efficient frontier, from what we can see on this graph. And very importantly for ML engineers, developers, this is having a higher efficiency in generation. Every token generation takes 0.19 seconds compared to the other methods, which takes at least 0.02 seconds. And there are a lot of reasons why this method produces less, or rather takes up less time to generate. I'll leave that to your interest if you are interested in the paper. And that is chiefly due to the fact that we do not need to do sorting. We do not need to do sorting, right? Sorting is at least order n log n, right? So in this case, we do not need to do sorting because we do not need to sort the tokens like top k. I need the top k tokens. No sorting required. So it's quick, easy, and fast. And the P-less method is also more able to discern between befitting tokens, right? As what you could see in the chart earlier, it selects the top 4 tokens. That makes more sense. And due to this trait, it produces generations that are not growing exponentially with increasing temperature. If you look at this table, for other methods like epsilon sampling, min p, Myrostat, top p, all the generations length exponentially explode when you increase the temperature. 113 words to 200 to 700 words, right, for this data set. And the same here, 500 words to 1,000 words, whereas pillars increases only marginally. Right? As you increase temperature, it still gives you a controlled generation with good accuracy that you saw 1 or 2 slides ago. Right? So let's recall, why is this useful? Why is pillars method useful? It's a method that really improves output reliability. It improves the accuracy of those generated outputs. It is efficient in generating outputs. The lengths are concise. And for us who are in the ML engineering and developer space, we do not need to tune the hyperparameters. Right? You do not need to report experiments that run over data sets, run over the decoding parameter like what you see in top K, top P, etc. There's no edge cases. Pillars guarantees a valid sampling set. There is no further noise added to the decoding process because pillars does not assume any particular distribution. It takes the empirical distribution. It can be a direct add-on to your LLM, as what we have seen in the earlier slide. And it can be used for many tasks, including your AI-assisted coding. And very importantly, it is not just an AI or ML practice that works. It is grounded in theory. So if you are interested in how to apply this code and in the research work itself, feel free to look up our resource. With that, I have nothing else for you except for answering your questions if you have.
Yeah, thank you so much for that. Introduced a whole bunch of stuff.